Yes, I slightly changed the title, so I will talk about the deformation and fracture of composite polymer particles. It's mainly the metal-coated polymer particles. So again, that's for the new audience. I'm from the Norwegian University of Science and Technology in Trondheim, Norway. Here are some facts about our university. But in this conference series, that's our logo is probably the 20th European Conference on Fracture 2 years ago in Trondheim. So here the outline of my talk. I'll first introduce you this Norwegian particle technology and its new application and challenges. Then I will introduce you that experimentally how we measure the deformation and fracture of the particles, and also using the molecular dynamic simulation, how to simulate the process. And then concluding remarks. Thanks to our former colleague, Professor John Ugostad, he invented a method to fabricate the monodisperse polymer particles. Size ranged from nanometer size up to even millimeter size. The key process is that we start from uniform seed, but then different with the seed polymerization, we will have the multiple swelling process. So every process, we control the swelling ratio of the monomers. Then at the last polymerization part, we get a uniform size of the polymer particles. So these particles, usually it's the cross-linking structure. And here I give two examples of the particles prepared by Ugostad method. You can see with 5 micrometer and 25 micrometer that we can well control the size distribution. And even comparison with the conventional method, we have a very good size control with the direct distribution here. And these polymer particles have been used very successfully in the biomedicine field as the template for the medicine design. But recently, the Norwegian industry has the new idea how to use these polymer particles. And by deposit the thin metal coating, usually around 100 nanometer thick, this particle will become conductive. And at the same time, I will keep the compliance, mechanical compliance of the polymer part. So we can use these particles in the component in the electronic packaging called conductive adhesive, which is the part in your mobile phone or your LCD of the PC screen. And there is some numbers here that's in this 3 centimeter long the circuit, we have around 3,000 pies. So each pie size is around 30 micron. And this is how one pipe looks like. So we have the particle here, usually between 3 to 10 micrometer, with the very thin metal coating around 100 nanometer. And in this process, you could see that the particles stay here and suffering the pressure, current, and heat coupling fields here. So how the mechanical integrity behaves will definitely influence the conductivity of your component and also the heat dissipation in the process. And in our investigation, we have found different types of the fracture model of these metal-coated polymer particles. So it's important to know or to design the single particle behavior. If we can predict and optimize single particle behavior, then we can have a better design of the whole component. And how to measure the single particle size with the macron size? Some people already mentioned the conventional nano indentation. We will have a sharp indenter penetrate into the flat, initially flat sample surface. But then we just take it inversely. Now we have our sample is the individual particle. And if we can have some flat diamond punch, then compress this individual particle and use the high resolution of the nano indentation, record the force and displacement curve. Then we could measure the single particle behavior. And here are two examples, comparison of the pure polymer particles with the metal coating, 2 layers of metal coating. And we can see that for the particle measurement, we have very repeatable results during the loading segments. And when there is the metal coatings, 2 layers of metal coating, nickel inner layer to provide adhesion to polymer core and the conductivity, and the gold outer layer to protect the nickel layer and further strengthen the electrical conductivity. So we could see that we are able to capture the difference between the coated and the uncoated particles. When there is the coating, initially that's the particle mechanical behavior is highly strengthened until some moderate displacement level. Then the displacement burst coming out, sometimes we also call it pop-in, and it corresponds to the coating fracture. After the complete fracture of the coating, so the coated and uncoated particles behave identically. And if we see it a little bit more clearly, that we compress the individual particle to different load level, then we combine with the SAM observation, we could see this fracturing process of the single particles. And there is the coating cracking here. And even at a very high load, we see the fracture of both the metal coating and also the polymer core. But it's very difficult to see here that the coating and the delamination of the coating from the core, which one is first. So we did a further investigation using the 3D X-ray imaging. Just have the X-ray, very strong X-ray beam come, and then we have the loading module here, which can rotate 360 degrees. And then we monitor all this compressing process. Later we do all the integration of the images. So we get a 3D image during the compression. And we can see that this process here is the top view of the particles cross-sectional direction. So you could see actually that before the cracking, the delamination first happened. And then the cracking also happened here. And some detailed the snapshots can be seen here. And this in the experiment, we could use different methodology to investigate the particle behavior. But then we also want to know that computationally, if we can repeat the process. So we have done the cross-graining molecular dynamic simulation. Here first, make the polymer particles, use the cross-graining model, and then deposit very thin nickel layer onto the polymer core here. And then let the system relax automatically. So finally, that those nickel atoms will form nanocrystalline structure on the surface. And then we just simulate the nano-indentation compression. Here is the stress, the stress strain curve with different thickness of the nickel. So we can also confirm that the metal coating strengthening effect to the polymer particles. And if we see the animation, this cracking process. In the experiment, we only have this snapshots, the cracking process. But then in the simulation that we see, the crack always happen at the equator and then propagate along the longitude direction, perpendicular to the compression. And after the cracking, the polymer chains coming out. Because here we have polymer chains, they can freely move. It's a linear polymer chains. And then if we compare this cracking process, this is by the in situ SAM compression with the nano-indentation module. So you could see it's the virgin particles, then some small crack happened, initiated at the equator and propagate along the longitude direction. And the final cracking here become almost like a pancake, and similar behavior happened. And then in the molecular dynamic simulation, we can repeat this experimental cracking process very well. Of course, there will be the scale difference. Here we have the particles only 10 nanometer size, while here we have 4 micrometer size. And coating thickness 100, here coating thickness only 1 nanometer. Yes, so come to the concluding remarks. We have this metal-coated polymer particles, and we have a very novel application in the conductive adhesive. anisotropic or isotropic conductive adhesive. So, but then the mechanical integrity or the structural integrity of these polymer particles is important for us. So we are able to use different methodology to do the mechanical characterization of the individual particles. Here we can see that the same particles before and after the compression, how it look like. And then using the molecular dynamic simulation, we are also able to fabricate this polymer particle model with the metal coating and then run the simulation part. Here is my collaborators and the funding resources. Thank you for your attention.